Hi everybody, the purpose of this video is to present the graph of the sine and cosine functions. But before we do so, I would like to talk about the idea of a periodic function. A periodic function is a function, I'm going to call it f, such that f of x is equal to f of x plus some integer multiple of a number that I call t. Okay, and this has to apply for every single value in the domain of f. It also has to apply for every single integer n for some fixed value of t. And here is an example of a periodic function. And what I'm hoping you can notice is that, yes, this thing actually does repeat. It repeats whenever t is equal to 2, or this equation is satisfied when t is equal to 2. It's also satisfied when t is equal to 4, or when t is equal to 6, or when t is equal to 8. Essentially any even integer satisfies this equation. However, the period of the function, which is or the fundamental period of the function will be the smallest value of t that satisfies this equation. So in this particular case, our period is this function has a period of 2, and we usually just say that t normally corresponds for the period is going to be equal to 2. Now, why is this important? Well, it turns out that sine and cosine are periodic functions. Recall that sine is the y value on the unit circle. So as the angle, as theta increases or decreases, sine is going to travel around this unit circle and then begin to repeat once it's gone through one circumference. Okay, the cosine will do the exact same thing. Cosine will travel around the unit circle as the angle increases or decreases and then repeat every value of 2 pi. As a consequence, both sine and cosine satisfies the periodic relationship that we mentioned before, and the smallest value of t that they would use is 2 pi, and we can say that sine and cosine are essentially periodic functions with period 2 pi. And here is our graph of sine. Notice here's when theta is equal to 0, y is equal to 0, so we're here. As theta increases, we travel up the unit circle till we get to 1. Once we're beyond 2 pi, we come back down to we come back down to 0 at theta, and then we continue, and then it repeats. As you can see, the domain is the entire real line. It never takes on any values greater or less than -1, so its range is between -1 and 1. It is continuous over the entire domain, and it will cross the x-axis at integer multiples of pi. And as you can see, yes, the period actually happens to be 2 pi. Also, we can notice that it is symmetric about the origin. And since it is symmetric about the origin, it happens to be an odd function. What else can we say about this? Well, the sine function is related to the unit circle as follows. Its arguments will consist of the angle measurements associated with the unit circle or the corresponding arc length, and its value always is going to be the y coordinate on the unit circle, which once again explains why it will never get higher than 1, it will never get lower than -1. Okay, so that's the sine function. Here's the cosine function. It looks hauntingly similar. Remember, the cosine function is just the x value of every single point on the unit circle. Of course, when theta is equal to 0, we're on the x-axis, so it takes on the value of 1. When it gets to pi over 2, theta is pointing up the y-axis, we have 0, -1, 0, and back to 1. Its domain here is also the real line. Its range is also between -1 and 1. It is continuous over the entire domain. However, its x-intercepts are at odd multiples of pi over 2. And that's pretty much what I'm trying to say here. This, of course, is pi over 2. And this is how you define an odd number. Take any number you want, multiply it by 2, add 1 to it, you have something odd. And as I mentioned before, it happens to have a period of 2 pi, just like the sine function. All right, now, unlike the sine function, the cosine function is an even function. Why is it even? Because it is symmetric about the y-axis. As a consequence, cosine evaluated at negative value is going to be equal to the same to the cosine defined at the positive version of that particular value. How does the cosine relate to unit circle? Well, once again, its argument consists of the angle measurement or the associated arc length. But in this case, the value of cosine corresponds to the x-coordinate, not the y-coordinate. And as a consequence, the graph of cosine is actually nothing more than the graph of sine shifted to the left by pi over 2. If I actually took this graph and I moved it over here, I would have the exact same graph. Okay, so why are periodic functions so important? Or why do we care about that? Well, there's lots of reasons, and this is just one of them. And this is the idea of what's called a Fourier series, which was discovered by this guy named Joseph Fourier. Actually, it's René Baptiste Joseph Fourier. Yeah, he's French, lived a long time ago. And what he showed was that any periodic function is nothing more than a weighted summation of sines and cosines. Okay? So it would follow this relationship where these happen to be Fourier coefficients, which you can compute once you've taken a little calculus. How does that work? Well, let me show you. Here is our basic function. This is the one that you've seen before. It's a different scale, but it's basically the absolute value of 1/2 pi sine. All right. Now, this is the first term of its Fourier series. Of course, the first term is always a constant term. In the electrical engineering world, we always called that the DC term. This is the first two terms, and really, this is nothing more than this added with one sine wave added to it, or cosine wave added to it, and that's pretty much what we have here. We obviously are missing a lot here, and we're kind of close here. Well, here is what happens when you add the third term. We're getting a lot closer here. We're getting a lot closer here. We still have a bit of an error there. If I added two more terms in this Fourier series, I will get this. And notice now we are getting very, very close. At least in the upward hump here, where it's nice and smooth. Down here, we're still a little bit off, but we're getting closer and closer. Now, if I continue to do this, and I got to the point where I used actually 100 terms, you can see we are extremely close. And this is basically one example of how the Fourier series works, and one application that and one consequence of the fact that any periodic function can be represented by a weighted summations of sine and cosines. And that's all I have for this particular video. If you have any questions, please feel free to contact me. This is Bob Boyle, signing off.